Welcome to learning about exponential growth and decay. The formula in general that we use when we deal with exponential growth and decay is a function a of t equals a sub 0 times e to the kt. A sub 0 can be read as a sub 0 or a naught and is the value when t equals 0, so it's the initial amount. We're using base e, but the base can be any number b. Using a different base merely changes the value of k for that base. So k is specifically found for the situation that you're working on, and then you use that k value to solve what you're trying to solve. This is basically the same formula as the one we learned last time, a equals p e to the rt power. So you really don't need to memorize two totally different formulas, just recognize the pattern of the formulas. P is the initial amount of money or principal, A is the initial amount of something, of population or radioactive isotope or whatever we're dealing with. E is our natural base, R is the rate when we're doing continuously compounded interest. K is like a rate. We call it just the constant value. And then T is T for time. So for money, T is pretty much always done in years. But for exponential growth and decay, T is whatever value we use to find K with. And then we have to stick to that value. So if we find K by using T in minutes, then we have to solve the problem using T in minutes. Or we get an answer for T in minutes. If we use seconds, then everything is in seconds. If we use years, then everything is in years. So it just adapts to what's happening at the time. Okay, let's look at example 4. In order to perform arthrosclerosis research, epithelial cells are harvested from discarded umbilical tissue and grown in the laboratory. A technician observes that a culture of 12,000 cells grows to 5 million cells in 1 week. So I feel like our time unit is going to be weeks. But maybe not. Let's keep reading. Assuming that the cells grow exponentially, find a formula for the number of cells in thousands after t number of days. Okay, so the unit they actually want us to use is days, but the first unit they give us for time is week. So I feel like we need to stick to t being in days, which means for the beginning problem to find k, we're going to use t equals 7 for the week, right? So what we do first is we find k, and we do that by using our initial numbers. So a culture of 12,000 cells grows to 5 million cells. So let's compare those two numbers really fast. We have 12,000 cells when t equals 0, and then we have 5 million cells when t equals 7. Now it suggests that we're going to find the number of cells in the thousands. That's just going to help simplify our problem a little bit from the beginning if we go ahead and talk about everything in terms of thousands instead. So we're going to go ahead and get rid of 3 zeros on everything. So then we would just call this 12,000 without writing the zeros. We just know our answer is going to be in thousands. And this one, instead of calling 5 million, we would call it 5,000,000, which is the same as a million. Okay, let's go ahead and use our formula. A as a function of t equals a sub 0 times e to the kt. We're trying to find k. That's our goal right now. So these types of problems always are kind of two problems in one. One problem to find k and one problem then to solve the question. So before we even look at what we're trying to find, ultimately we need to find k. So let's go ahead and plug in the amount we have at day 7, which is 5,000,000. Doing this in thousands, so I'm just going to write 5,000,000 instead of 5 million. And then for a sub 0, we have 12,000, so we're just going to use the 12. Everything's done in ratios anyway, so it's not a big deal. And then t is 7, so we have 7k. Okay, let's go ahead and solve this the same way we did these in our last videos with money. We're going to divide that 12 from both sides to isolate our variable. So when we divide that by 12, that reduces, if you want to, you can change it to a decimal. I'm just going to leave it as a reduced fraction. You could even leave it as 5,000 over 12 if you wanted to. But it does reduce to 1250 over 3 if you'd rather. It's all a ratio. It doesn't matter whether you use the original ratio or the reduced ratio or a decimal. However, a decimal would matter a little bit here because if it's thirds, the decimal will not terminate, so it's a little bit harder to get an accurate result if you use a decimal in this problem. You can still do it, just use a lot of decimal places. Okay, so next we're going to take the natural log of both sides. Natural log, natural log. Remember we use the power property. Sometimes I like to skip steps here because it's just all the same thing in every problem, but I'm going to try to avoid skipping steps. So we have the natural log of 1250 over 3 equals 7k natural log e. I just used the power property to bring the 7k to the front as a coefficient. Natural log e turns into 1, so timesing by 1, it goes away. So k is going to be equal to the natural log of 1250 divided by 3. So that whole thing is in the log, and then we divide that by 7. So at this point, yeah, you're going to get an approximate decimal, and there's really nothing you can do about it other than to use an approximate decimal, unless you type this big whole thing in your calculator when you go to use it to solve the rest of the problem. So that's fine. If you want to avoid errors, you can just literally type in this exact value every time you need to use k in your calculator. Or you can do an approximation with as many decimals as you feel like using. The more you use, the more accurate your result will be. Okay, I'm going to go ahead and group this and move this out of my way a little bit. Now that I've found k, I can go ahead and solve the question that's being asked. So the question is, assuming that the cells grow exponentially, find a formula for the number of cells. Oh, we're not actually solving an actual problem, so we are done. All we are doing is finding a formula. So A of t is 12e to the 0.861t, and that is for t in weeks, t in days, and cells in the thousands. Since we knew that's what we were doing, we maybe don't have to write out that clarification, but it's good to make sure our reader knows that in case they're going to use the formula to actually solve something.